Welcome back to Element 14 Presents. I'm Clement. Have you ever wondered what's running all the heavy machinery out there? PLCs, programmable logic controllers. Yep. They're how expensive? How can that be? There's only one way to find out. So you find multiple types of programmable logic controllers or PLCs on the market. Sometimes they are actually just an Arduino in a fancy box and with some relays. So there are also legacy systems with big brand names and high price tags, and these are built for reliability and never change a running system. So sometimes they are a bit outdated. And then there are some new players. Even Arduino now makes proper PLCs. But I'm not just showing you their PLC and whatever. I'm sure these are awesome. I haven't tried them yet. But I want to get first-hand experience and hopefully show you the difference by building one myself with my own choice of components that I think will fit the application. And we do it 2 times. So of course the big name brand systems will have their place for all their proprietary, super reliable stuff for safety critical operations and whatever. But I don't want to get locked into vendor lock. I want to have an open source solution. So I'm basing my design out of open source designs or open source parts. And one of the most open source single board computers that I can use to run my PLC, because I want it to have like serious capabilities, is a PocketBeagle 2. We've used that in a previous episode, and I'm quite fond of that little guy, but it has a steep learning curve to be used because this is professional embedded engineering. This is not just slapping a Raspberry Pi into a fancy case and putting it on a DIN rail. This has some more to it. So I have decided that my PLC will have to run Linux in a special way. I want it to have real-time Linux support, and it also should have a deterministic way of controlling their inputs and outputs, which is usually microcontroller territory. I've used the PocketBeagle 2 specifically for its capabilities in that regard. It runs a real-time Linux kernel, Debian 13 is the distro, and then underneath it, so there's a Citara AM6254 processor on the board, which has a core that runs Linux, but also 2 real-time cores called the PRUs, the programmable real-time units. They're exactly made for these purposes. And we have redundancy basically built in, we implement it in software, which means we have a real-time core that could control all the inputs and outputs, keep the machine alive, and make sure that everything runs as it should. We have the Linux controls. Those run USB devices, high-level stuff like AI models even, and the communication with network and other devices. And they can communicate over shared RAM, which is, to my knowledge, the fastest way of data exchange between a high-level Linux system and a microcontroller. And there's a second PRU core, and we can use this one either to build redundancy, so there are actually 2 controllers controlling the machine and checking each other for errors or taking over if one fails. And they can also check if the Linux system stalls or halts for some reason. Or we could use the second one as a watchdog to make sure that everything is in order. And once it deviates from all the expected states, it will, in nanoseconds, do the alarm and make sure that our machine behaves safely. So these are the redundancy systems that are built into the really expensive programmable logic units. Difference is we have to do all this functionality from scratch. There is a metric buttload of parts ready for my project. So I'm building it once with stuff that I already have on hand. The way just any maker would do it to make a DIN rail mounted Linux computer that runs a machine. And then in the second version, I try to apply some professional engineering that I hopefully learn about in the meantime. So of course I have to put my device into a professional case. This is a Hammond 1597 DIN rail case. This is available in a lot of options and with fancy covers for all the ports. I didn't order the covers yet because I don't really know how they would fit and which bits I'm gonna put where, but that doesn't really matter because Hammond provides CAD files for these. And so I can 3D print them, see which ones fit, and then order the right ones. I will make both versions fit this case, of course, but in the first version I will try to use only the PDF data for the shape of the PCB and try to eyeball the things to get it done as fast as possible. The maker approach, just make it work good enough. Behold, Eisler has conveniently shipped me the cheapest version that I could make on this. This is the cheapest service they offer in the most standard way, 2 layers. This is what I came up with. I eyeballed the position of all the connectors and I tried to put, typical maker way, as many features in here as possible as I want to use. So I'm using analog input capabilities of the PocketBeagle, which, for example, a Raspberry Pi doesn't really have, but this one has a 12-bit ADC, so of course I want to take advantage of it. It has USB ports broken out on the expansion pins, so of course I put in a microchip USB 2514 USB hub, which means I can have 4 USB ports. I put 2 on here. I wanted to fit 3, but they quite don't really fit. So I put one on the inside and one on the pins on the top. So I don't know what I'm gonna use them for, but hey, they're there. And of course, 4 relays, because we want to switch big loads. These are capable for 230 volts AC. And of course, I could also switch 24 volt loads with it. So quite a lot of capability, small package, and this was done very quickly. And in the schematic you see it's as simple as possible to just make the whole thing work. And this would be fine for just making some hobby project work in a first iteration. But this is not fine for a PLC. Quick word on safety before I dive into the design. I would not want to touch any of the relay adjacent components while this thing is in operation, just because there is no real isolation in the original design. So that means in case something goes wrong, there could be potentially 230 volts everywhere in the system. So this makes me very uneasy. That's something we have to address in our new design. Oh, and also the USB ports are very simply designed. It's basically the bare minimum to make that hub work, but a proper USB implementation looks a lot different. The professionals have called and they declared you have to fit the right parts on your board for the right purpose. So of course this time I'm ordering the right parts exactly for my project. So I'm using vertical USB ports that actually fit, and I even discovered that the screw terminals are not created equal. The ones I used in my original design are 1 millimeter thick to fit that case. Turns out the actual industry standard is 1 millimeter less bulky. So with the right parts, I can also now leverage the manufacturer's CAD data for the correct outline of the board, of course, but also for the perfect fit of the components with the actual connector pieces that then will cover the bits you're not supposed to touch. So you can take advantage of all the data the manufacturer gives you. Keep in mind, these are basically pretty raw CAD data for measurements. You can't just make a knockoff of the design by using these, but what you can is you can 3D print representations of them. So I now 3D print all the versions of the covers that they had and make sure that my outlines will exactly fit those covers. So here's my professional or professional adjacent version of the design. I've used Eisler again, Enig finish, 4 layers and Blitz service to get it here in time. I'm also switching to the PocketBeagle 2 Industrial, which is pretty much the same thing, but it has eMMC on board and is a bit more hardened and it's red. So this one will fit on here. It's the same USB 2514 USB hub by microchip. I fitted 2 ports. I originally wanted to have 3 ports, but I just couldn't make them fit so they would also fit perfectly with things plugged into them, because sometimes USB sticks and whatever can be a bit wider, so I have to make sure that this will fit all the devices. So I'm not cramming them in there, and also assembly should work still automated if we're gonna produce this thing, so I always have to make sure that I make the right calls for reducing some features. USB is completely differently implemented here. On the original design we didn't have any ESD protection, nor did we have overcurrent protection, but this is necessary to have a compliant USB design, because these have to restrict the current they are supplying to the devices to a safe level, and they have to detect if something goes wrong. So your device that you plug into these USB ports can't destroy the overall thing or inhibit operation, which could be very dangerous in a machine controller. So these have current control chips on there that I specifically ordered. And of course this design now takes up more space, and that is why I have reduced the total amount to 2 ports. I left the other 2 in my design because maybe I want to do a bigger version down the line in a bigger case that has 4 USB ports, and then I could fit them. Now for all the analog routing, I've made a crucial mistake in the original design. I've routed my analog ports right next to the relays. That will not work very good because they will couple into it. The sparks that the relays will have when they trigger, those could easily couple into analog lines, give me wrong readings or even erratic behavior. Or they could even fry my microcontroller because the analog lines are directly coupled to the ADC inside my PocketBeagle, and that could potentially damage a lot inside the board if a spark goes through. Which also brings me to the next thing, the separation layer here. This is a separated board. It's not all in one. This is actually more like 2 PCBs next to each other, and they are connected only over this part. So what? Why do we need some separation between these parts? Well, one of these will deal with high voltage, and by high voltage I don't mean actual high voltage, because high voltage is, in terms of legalese, voltages in the thousands. What I actually mean is low voltage, but not low voltage as in 5 volt, 12 volt, 24 volts. These are actually outside of the low voltage directive. I know the terms are confusing, but low voltage is actually over 50 volts DC or 75 volts AC. So any relays that deal with 230 volts, these will fall under the low voltage directive. Yeah, I know, confusing terms. But anyway, we have to make sure that our relays, which can be used for 230 volts, but also 110, 48 volts, 24 volts, 12 volt systems, it doesn't matter, that these are safe and they don't have any negative effect on the control side of our board. So what we have to do is clear separation between the two. I have basically made a slot here. You can make a real physical slot. In this case, I opted for just separated planes, and also the solder mask is removed, so I have clear indication on where that line is. And so it's basically in one board, but it's actually 2 separate boards on one piece of FR4. They are only connected with a TIL 199 optocoupler. An optocoupler is a way of galvanic isolation, meaning there is no actual direct connection between these 2 halves. It is just and only a connection by light. So there is an LED in one end and a phototransistor in the other one. If the LEDs goes bright, then the phototransistor will be activated, and that allows us to control our relays on the second side of the board. But they also need power, right? These relays work with 5 volts. And of course there's a relay driver involved, the ULN 2003A. So how do we power these without re-establishing the connection? In the moment I would connect 5 volts just from the other side of the board and the ground signal, then they would be connected again, and all the bad signals that we don't want to jump over could take this path. And even if we have external power supplies for both, which we have in this case because these have their own power connections over here, then if we would connect them to the same power supply, we have that path again. So what we need is truly isolated, independent power supplies. DIN rail power supplies are really handy for that. I use one by Multicom to run my logic, and I use pretty much an equivalent model by Meanwell to run my relays, just to have 2 different ones. And I can spot them easily on my DIN rail because they have different colors. but they are equal in terms of what they can do, and they are both fully isolated, which means if one goes bad, the other one isn't affected, and there are no signals going in between those two halves of the board. We're truly isolated. There's quite a lot going on the board. Did you notice that I preferred having good layout instead of more features on there? Because that is what the professionals do. The most important bit is safe and reliable operation. If you need more features, you can always add more stuff to the outside. Additional units, additional expansion stuff that you can connect over I2C or other connectors. So you don't have to cram all the features inside, only the ones that you actually truly need. Now I have very modest expectations for my design. I just want it to run Linux, make an analog reading, interact with a USB device, and interact with digital I/O, like activate one of the relays. I know there might be some problems because I'm using a lot of unfamiliar parts for me. I'm going into more professional engineering territory with more components and more opportunities to go wrong, and I'm on a time crunch. So these are bound to have issues. Usually you don't build these devices on the first try correctly. The important bit is that we learn from it. On a Raspberry Pi or Arduino, the easiest bit is just pulling a pin high and low, the first interaction that you do to blink an LED. On an embedded system that you get for integration into whatever you're building, you're not in the realm of convenience. Raspberry Pi is so popular because they do a lot of the work for you and you just have to use it. On BeagleBone, it's a bit different. They prefer flexibility and the possibility of building whatever you can envision and put in the work to make it real before any convenience. And like in case they are also saving on having to support like all the bits upstream, so they can have like a bare bones basic Debian distribution for their products and don't supply them with the exact configurations that are needed for the IOs to use. You have to do that yourself. I learned this the hard way in hardware. At the point of when I'm doing this, the documentations were very incomplete and not in a good shape. I hope that this has been already fixed by the time this video gets put out. I do believe there's a big will and push to do this, but just in case, what you need is all linked in the show notes. I've put up a GitHub repo with some steps that should help you get this all working. The point is device tree overlays. Embedded Linux systems like the AM6254 by TI are basically bare bones processors that can have a lot of different functionality in them. All the pins can be configured in vastly different ways, and this gives you a lot of flexibility. But also, it makes you put in the work to connect these. So device tree overlay tells your Linux OS what pins are where and how to use them and how they are connected physically and in the code. So first you have to write a device tree overlay, which is very intimidating and complicated, and I don't even halfway know what I actually did there. Basically, I copy-pasted other people's work and hoped for the best. But once I got this compiled, and yes, you have to compile this on the PocketBeagle itself, then I could interact with the pins. And for the analog reading part, that actually works from within Linux because it already has a subroutine that reads an ADC, a 12-bit ADC in that case, and gives us the voltage readings. That's something you can't directly do with a Raspberry Pi. You need some additional hardware for that. So either you prefer the ease of use of a Raspberry Pi, or you prefer the flexibility and the freedom that comes with a PocketBeagle or a BeagleBone, but be aware that there's a steep learning curve and you have to put in a lot of work to make things work. Yeah. One of the really cool features that the PocketBeagle has are the programmable real-time units, of course. This is basically microcontrollers inside the processor that can act independently. Very hard to use from a maker perspective, very cool and flexible to use from an embedded engineering perspective. So if you are ready to dive into that rabbit hole, and be aware it is really a steep dive, then be my guest. It's awesome. And the feeling when you finally get that pin to blink is great, but boy, does it have a learning curve. And of course, after a while I got my GPIOs to work, but they didn't work as expected with the relays, because I made a few bonehead mistakes. If I measure my pins going high and low, I basically made a little function that toggles it high and low every 500 milliseconds. Then I could see the pin going down and up again, but only between 3.3 and 2 volts. And this is because I used the optocoupler like a normal IC where I just directly connected to the line. But optocouplers have just LEDs inside and phototransistors. So that LED needs to have a current limiting resistor based on the voltage level that I use for my I/O. And with a 3.3 volt logic level, I should have used a 330 ohm resistor, and also a pull down would have helped. But I didn't implement either of those, so now once the LED activates for the first time, it sits there drawing current at about 2 volts and never deactivates again. So I can't use the relays for my demonstration, but I can use all the other bits. So here we have my demo unit. So this is our PLC. I've even used my laser engraver to professionally engrave all the things on here. This is done the same way as on these ready-made power supply units. So this is also done via laser engraving. I haven't found the perfect settings yet, but I'm getting there. It looks quite awesome. So these are my power supplies, either 5 volts from 230, one by multicomp powering the logic. The second one was supposed to power the relays, so now it's disconnected. I've used 3D printed inserts because I didn't order the right covers, but these are made from the same files that Hammond gave me for the case. So that means if I order the covers, then they will perfectly fit. Over here we have our power inputs and our analog inputs, and I have 2 trim potentiometers over here, so I can easily regulate the analog signal that is coming in here. Then we have a dongle for network connectivity, so I can look at all the stuff on there over the network, and a USB camera. And this will now allow me to run a little demo where we use the USB camera for a live feed, analyze whatever we see in that camera. Specifically, we're looking for a specific color. We can set the hue and the saturation with these analog potentiometers on the fly and observe the stream over the network. In my little demonstration, you can see me adjusting the analog inputs in real time just with a little screwdriver, and once we have adjusted correctly, it correctly detects the blue color of my shirt. Of course, it's in Australian mode, so for our viewers on the northern hemisphere, I will use a little post-processing trick in the video editing to make it convert to northern hemisphere standards. Anyway, one thing that I'm quite fond of, that I'm missing with a lot of professional PLCs, is the ability to use a standard electrician screwdriver for all the terminals. Sometimes they have smaller ones or even special screwdrivers that won't fit this one. So now that we know how incredibly difficult it is to make a real PLC, a system that has redundancy, safety watchdogs, and all these constructive features to make all the relays safe and all the connections and inputs reliable, I think we can appreciate that sometimes they just have to cost more. And if we open them up and take a closer look at them, we can also put others that might be overcosted under scrutiny and show if they're really worth their money. And I hope you do. In case if you have any ideas of machinery that we could use our homemade PLC for, let me know on the Element 14 community. You can go there, of course, to find all the files and whatever you want for all our projects. I gotta go. There's another project waiting for me.